Okay, we're going to continue on with Unit 17 here. Taking a look here at figure 17.31. This is a diagram of a three-phase power supply, or fairly similar to what you would commonly see inside of a three-phase panel, breaker box. So if you take a look inside that box, usually you've got line 1, line 2, and line 3, or rather phase A, B, and C, connected up to a three-phase breaker. And usually it'll be every third bar going vertically there. So the first bar would be the A phase, the second bar would be the B phase, and the third bar would be the C phase. And then the breakers are designed to connect on each side with that. But in this case, how they've got it drawn here is fine. So if this circuit or this service here, it appears that it's a 230 volt, 115, 230 volt, three-phase service. Quite possibly that could be a delta, but they're not demonstrating the wild legs. So anyway, with that there, from line 1 to neutral, they're getting 115 volts. From line 2 to neutral, they're getting 115 volts. And in this case, line 3 to neutral, they're getting 115 volts. Be careful here. That's not always the case. If you have a wild leg in a delta system, you might have a 208 volt line 2 to neutral. It could be 208. Usually it's in the center, but they did some stuff that was different years ago, so keep that in mind. And then further stated, the high voltage connections from line 1 to line 2, 230 volts, 2 to 3, 230 volts, and then 1 to 3, 230 volts there. So you can get some different combinations out of different supplies, whether they wire it in Y configuration or delta configuration, so just be careful with that. From the three-phase power supply, you can have a three-pole breaker to get 230 volt three-phase out of it, which connects to all three phases in that breaker. You can connect a single-phase breaker, double pole, and get 230 volt circuits out of it. Or you can have a single pole breaker and connect it to any one of the lines, depending on, again, being careful of the wild leg, if that is in there. You can get 115 volts out of the breakers, out of the circuits. In this figure 17.32 A and B here, what you're looking at is a three-phase power supply diagram, three sine waves, if you will, on that. So if we take our standard single-phase circuit here in the black wave, you would notice that it is 360 degrees, 60 cycles per second. But when we have three-phase, each phase, A, B, and C, black, blue, and red, they are all 120 degrees out of phase with each other. And therefore, it gives you a already made rotating magnetic field for your motor. So if we take one point in time, these other two phases would create more pull than the black phase. Or if we take it at a different point in time, then the black phase and the blue phase would have more pull than the red phase. So with that, we can have a already made rotating magnetic field inside of the B figure here, inside our motor. And this motor is wired for Y, where they connect to line 1, line 2, and line 3 to the three different phases and three equal windings in that motor. In order to reverse this motor, all you got to do is change any two of the three leads. Commonly in the field, though, is T1 and T3 to be reversed, and the rotation will reverse. So here we've got the next diagram, which is the same thing as I was discussing on the previous diagram there, 17.33. That's just what they're doing. They're reversing any two of the three leads. They chose to do line 1 and line 2 here, probably for editorial purposes or for the drawing here. Real easy to do. And that motor will reverse direction compared to the previous diagram on that circuit. So relatively a simple motor, a three-phase is. These two motors here, this one and the last one, they are a single voltage rated motor. We have not gotten into wiring them for dual voltages yet, but that will be along in a different video. So I've said it before and I'll say it again. The book likes to jump around a little bit, so we're switching gears here again. What we're looking at here is the internal makings of a refrigerant compressor, which we'll learn more about in air conditioning coming up. But With this here, it is a hermetically sealed compressor. Basically what that means is your motor is embedded or is welded in a shell that we do not have access to. So you can see the windings in here, and you can see the rotor, and the shaft is connected to these pistons down here, which move up and down and then pump the refrigerant throughout the system. So anyway, like I say, we're kind of jumping back to the single phase yet again, and we're going to discuss a little more about the internal wiring of this particular single phase motor, how it differs compared to a standard single phase motor that you would commonly find on a drill press or a auger conveyor belt, something like that. If you recall, we discussed back in the single phase section here of the single phase dual voltage rated motors and the single phase single voltage rated motors that they have two windings, a run and a start. And then those two windings had a point where they would have been connected together. That's exactly what these terminals are coming out of the internal shell of that hermetically sealed compressor. We have a common terminal, a run terminal, and a start terminal. The challenge is determining which one is which because they're usually not marked as nicely as this one is out in the field. So let me go on to the next diagram and discuss that a little more. So internal, as we stated in that compressor, you have that run winding and the start winding, and they're connected at a common point right here in the center where the two come together, and they are brought out. As we stated previously, most single-phase motors have a start switch. Now, because this is a hermetically sealed compressor and the windings are running in the refrigerant, we cannot have a switch embedded in that refrigerant, otherwise the arcing will actually burn the refrigerant and it would not be good. So what we're going to do here is we're going to take some resistance measurements here. If we take our knowledge from the single-phase motor, we know that the start winding is going to be small gauge wire and longer in length. So therefore, it has high resistance compared to the run winding, which is a large gauge wire and shorter in length on that. So if we were to take our meter and we were to measure from start to common, it would have a value of, say, 10 ohms. We would know that the run to common would have to be something less than 10 ohms, say like 2 ohms or 3 ohms. And then the last thing we can do is we can measure from the run to the start, which if you follow that through, that would be all of the run resistance plus all of the start resistance. So therefore, once you have the highest resistance, you know that opposite those two terminals that you're connected to would be the common terminal on that particular single-phase compressor. From here, we're going to discuss how the start winding is actually taken out of the circuit if it's that type of motor. So before I get into how the start winding is taken out of that motor, I do want to discuss this here other figure 17.37. What you're looking at here is how the electrical connections get its connection from the internal motor leads to the outer portion of the shell where you can actually work with them. So here we have the outer portion of the compressor shell here, and inside there's an O-ring in between the insulation, and that will prevent the electrical connection from making contact with the metal shell of that compressor in there. So it's all kind of sandwiched together and molded in there, and again, we don't have access to these nuts on the inside of the system. We just got some spade leads, some terminals that we will push our connector onto. So as promised, I would discuss on how the start winding is taken out of that single-phase motor. What we're looking at here in figure 17.38, A and B, the A figure and the B figures here, is what they refer to as a potential relay or a voltage relay, right? Voltage potential on that. So here's a box of one that you can get some information on the voltages of it, the dropout. It'll drop its coil out at 90 volts. It'll pick up somewhere between 171 and 184 volts there, and it'll continuous at 336 volts AC. It'll activate its contacts. Moving down here, this one here is what one of the potential relays looks like when it's connected in a circuit there, and then here's your connection points for the terminals, which we'll discuss in a second. Further stated, here's the cutaway of it, the internal. As you can see, it's got a coil in there, and the coil activates some contacts fairly similar to many other relays. Here's the important thing that I really want to discuss with you. So I've blown this up a little bit. This is the wiring diagram of our potential relay. And the potential relay is actually in gray down here in its terminals. And as you can see, it's got a coil, a winding in there, and then the coil activates a set of contacts, and then the contacts will activate either the capacitor and kick them out and so on. So we got to break this thing down a little bit. What we're looking at here in this diagram as a whole is a single-phase motor that does not permit a centrifugal switch in the windings. Again, because of it being refrigerant, can't have it in there. Arcing will burn that refrigerant. So what we've got is we've got our power coming in, 115 volts, connected via a compressor contactor, which will do its main control. From there, once it receives power, we will energize the run winding with that 115 volts, and it'll engage that part of the circuit. Then we've got to deal with the start part, and this is the most confusing part of this. Previously, in the single-phase motor, we had a start winding, a start switch centrifugal, and a start capacitor and a run capacitor. This is all standard, hasn't changed anything. What is new is right here, how they added the potential relay. Because it cannot be connected via centrifugal force, we've got to energize it via voltage. The other thing that's interesting is that coil will open at a higher voltage than 115 volts. If you see here, we're measuring from the to 175 volts in order to actually open that switch. So if we look at that, what will happen is the power will come in through the start winding. It will supply its 115 volts there, and then in series with the system is your potential relay, your start capacitor, and your run capacitor on back. So we got 115 volts here, and then from across the 2 points, from here to here is 115 volts. But then we also get some additional, what they refer to as counter electromotive force or induced CEMF voltage, which will boost that voltage up to the 175 volts. Obviously, it's kind of difficult to get more than 115 out. But with the step-up transformer, if you think about that, primary being a smaller turn ratio compared to the secondary, we will induce that voltage in there, and then at 175 volts, it will actually pull that coil in there, disengage the contacts between terminals 2 and 1, and remove the start capacitor. So what is important here is how these things are wired. One leg has to be wired to terminal 5. Terminal number 2 has to be connected to our start winding and maybe the run capacitor. And terminal 1 has to be connected to one side of our start capacitor, and then there on back down the line. So it can be a little bit confusing, but make certain you take a little bit of time to understand the wiring of the potential relay based on these terminal numbers. Okay, I think I'm going to leave you on this one here with the potential relay. That's where we're going to stop for right now. And then when we pick back up, we'll go into a couple different deviations of this potential relay. We'll discuss the current relay and some positive temperature coefficient resistors that can also be used to disconnect in this case, the start circuit, the start capacitor in this one here, but it could also be utilized to disconnect that start winding as we did with our centrifugal switch previously. So the diagram will be a little bit different when we discuss the current relay on the next one and the other ones. So, all right, we'll catch you on that.